Welcome to this video where I take an example problem in the state observer design and solve it using the 3 different methods covered under the state observer design presentation. This is my design problem. We are told that a system is described by the state equation. So the state equation is given for a second order system, and the output equation is also given. And we have to design a full order state observer such that the eigenvalues of A minus GC are placed at S is equals to -5 plus or minus, is supposed to be plus or minus J5 root 3. So we design a full order state observer such that the eigenvalues of A minus GC are located at -5 plus or minus J5 root 3. So we need our matrix A, which is 0, 1, -2, -3, our matrix B, which is 0, 1, and our matrix C, which is 1, 0, for purposes of our design. I'll go through the 3 methods one by one. The first method is the direct substitution method. And in the direct substitution method, we said that first we need to determine the desired characteristic equation. The desired characteristic equation from the location of the poles of a given system. So in this case, from the eigenvalues of the desired system, which are S is equals to -5 plus or minus J5 root 3. Our characteristic equation can be written as S plus 5 minus J5 root 3 into S plus 5 plus J5 root 3 is equals to 0, which upon expansion, we obtain S plus 5 squared minus J root 5 root 3 squared is equals to 0, which will give us S squared plus 10S plus 25 plus 75, which is 100, is equals to 0. And that is the desired characteristic equation of the system. We choose our feedback gain matrix G to be G1, G2, this being a second order system, then G will be G1, G2. Then the characteristic equation based on the controller design will be Si minus A plus GC determinant is equals to 0, where our matrix A was defined by 0, 1, -2, -3, and our matrix C was defined as 1, 0. So we get Si minus A plus GC. We first need to get GC. GC will be G1, G2. GC will be G1, G2 multiplied by 1, 0, which will give us G1, G2, and then 0, 0. That will be our matrix GC. Then we take Si minus A plus GC will be S 0, 0, S minus A will be 0, 1, -2, -3 plus GC, which is G1, G2, 0, 0. The determinant of all this is equals to 0, which we can write this as S plus G1 for the first term, then -1 for this one, then G2 plus 2, this will be 2 plus G2, so 2 plus G2, Then we'll have s minus 3, minus 3, which is s plus 3. Determinant is equals to 0. Then we can expand this. We can expand this into the determinant to obtain s plus g1 into s plus 3 plus the terms of the minor diagonal, because of the negative, it will be positive. So plus 2 plus g2 plus 2 plus g2 will be equal to 0. Upon expansion, we get s squared plus g1 plus 3s plus 2 plus g2 plus 3g1 is equals to 0. This is the characteristic equation based on the modeled controller or the designed controller. If we compare this with the desired characteristic equation based on the location of the poles defined by s squared plus 10s plus 100 is equals to 0, the coefficients of s will give us g1 plus 3 is equals to 10, from which g1 is 7. Then 2 plus g2 plus 3g1, 3g1 will give us 21 is equals to 100, from which g2 will be 100 minus 23, which will give us 77. And therefore, our feedback gain matrix G is G1 7, G2 77. And that is the feedback gain matrix G that will ensure that the eigenvalues of A minus GC are as specified in the question. Method number 2 is using the Ackermann's formula. By use of the Ackermann's formula. From the Ackermann's formula, we know then that our matrix G will be defined by phi of A, n inverse, and then multiplied by 0, 1. By Ackermann's formula, our matrix G will be given by phi of A, n inverse multiplied by 0, 1. Our n is the observability matrix, which we should have determined previously, given by CCA, because we need to have tested for observability of the system. Our matrix CA will be obtained as the matrix CA will be 0, 1, negative 2, negative 3, multiplied by 1, 0, which will give us 0. So it's CA, not AC. This is AC. Should have written this as CA, which is 0, 1, 0, which is our N. This is our CA, which will give us 0, 1. Our matrix N will therefore be equal to C. C was 1, 0. CA is 0, 1, from which the determinant of N will be equal to 1, which is not equal to 0, and therefore the system is observable. So we should have tested for observability of the system before we proceed to determine the feedback gain matrix G. Our N is an identity matrix of order 2. Then phi of A is obtained from the desired characteristic equation of the system by substituting for S is equals to A as follows. The desired characteristic equation, we evaluated this. The desired characteristic equation, this was the desired characteristic equation, was equal to S squared plus 10s plus 100 is equals to 0. So our phi of A will be A squared, where there is S, we substitute with A, plus 10A plus 100, but because this is a matrix operation, we multiply by an identity matrix I to be equal to 0, and that is our phi of A. Where A is our matrix, 0, 1, negative 2, negative 3. That is our matrix A. We can evaluate phi of A in MATLAB directly and then solve for the matrix G given by phi of A multiplied by n inverse multiplied by 0, 1. We can solve for this directly in MATLAB and obtain the solution for G as follows. Our matrix A in MATLAB is given as 0, 1, negative 2, negative 3. That is our matrix A. Our matrix B is equal to, our matrix B is equals to 0, 1, 0, 1. Our matrix C is equals to 1, 0. Then our matrix N will be equal to C, CA, and C times A. Sorry, our matrix is supposed to be a square bracket, which is similar to what we obtained as N previously. And the determinant of N, we noted that this is not equal to 0. It's 1, not equal to 0. And we said that the system is completely observable. We can choose an identity matrix I of order 2 defined by 1, 0, 0, 1, 1, 0, 0, 1. That's our identity matrix I. Phi of A was defined as, we can call it P, to be phi of A, which is A squared plus 10 multiplied by A, 10 multiplied by A, plus 100 multiplied by I. From the definition of phi of A, which is A squared plus 10A plus 100I, we can evaluate this. That is our phi of A. Then our matrix G will be equal to phi of A, which is P, multiplied by N inverse. So we multiply by the inverse of N, and then we multiply this by a matrix 0, 1. We multiply this by a matrix 0, 1 to get our G. And as you can see, our G is 777, which is similar to what we obtained previously. So if we substitute for those values of phi of A, N, and then 0, 1, we note then by Ackermann's formula, G is 777. Lastly, we have the method number 3, which is by use of the transformation matrix. We are first supposed to determine the characteristic equation of matrix A. We determine the characteristic equation of matrix A as Si minus A determinant is equals to 0, from which we can write as S minus 1, 2, S plus 3 determinant is equals to 0 if you substitute for the values of A, and this will give us S squared plus 3S plus 2 is equals to 0. This is a second order polynomial in S, which we can compare with S squared plus A1S plus A2 is equals to 0, where A1 is equals to 3 and A2 is equals to 2. Number 2, we determine a transformation matrix Q that is able to transform the system state space model into observable canonical form, defined by Q is W multiplied by N. Q is W multiplied by N. Now, it's good to note that our W will be obtained as follows. So it will be A1, 1, 1, 0. That will be our W from our previous discussion. And this will lead to the matrix 3, 1, 1, 0. That is our matrix W. Our N is an identity matrix, and therefore Q multiplied by N will still give us W. Okay, so we are saying that W is 3, 1, 1, 0. Our N is 1, 0, 0, 1. And therefore, our Q will be W times N, which will give us 3, 1, 1, 0. Number 3, we determine the desired characteristic equation of the system. The desired characteristic equation, which we have defined so far. The desired characteristic equation is this equation, which is S squared plus 10S plus 100 is equals to 0. So the desired characteristic equation is S squared plus 10S plus 100 is equals to 0. Again, this is a second order polynomial in S, which we compare with S squared plus alpha 1S plus alpha 2 is equals to 0, from which alpha 1 is 10 and alpha 2 is 100. Once we have that, then we can write by the transformation matrix, our gain matrix G is given by Q inverse multiplied by alpha 2 minus A2, alpha 1 minus A1, which we can write as 3, 1, 1, 0 inverse multiplied by 100 minus A2, which was 2, so 98. That will give us 98. And then alpha 1 is 10 minus A1, which is 3. That gives us 7. Which we can again compute in MATLAB as follows. Let's define our matrix Q to be equal to the matrix 3, 1, 1, 0. Our matrix the next matrix is 98 and 7. This matrix, I can call it E, which is 98, 7. Again, back to MATLAB. So our matrix E, we can call it E, which is 98, 7. 98, 7. Then our matrix G will be equal to the inverse of the matrix Q multiplied by the matrix E. And as you can see, our matrix G is still 777. And therefore, the three methods yield the same value for the matrix G as 777. Those are the three methods for the determination of the feedback gain matrix G under state observer design that is able to help us locate the poles of the system at the desired locations. And that is the end of my presentation. Thank you for watching the video.